Welcome back to my channel. Today we're going to be talking about antiderivatives or indefinite integrals. To start off with, integrals are the area under the curve. We have the integral symbol, which looks like this. You'll see some people call it like a crowbar. It's the integral symbol. We have two types of integrals. We have definite and indefinite. It'll be really easy to tell the difference between the two because a definite integral has numbers or bounds. So we have a starting and ending value. And then our function. Versus an indefinite, which is just our integration symbol, our function, and dx. So when we want to find an integral, we would normally do that when we see the integration symbol, a problem that's starting out with acceleration or velocity and we need to kind of go backwards this time, or if we need to find the area or volume of a graph or situation. Antiderivatives are the opposite of derivatives. They are kind of interchangeable. The biggest difference is just how we write it. So when we write an integral, we use our integration symbol. When we say take the antiderivative, we don't necessarily have a symbol for antiderivative. So when we think about antiderivatives, we want to think about derivatives to kind of work our way the other way around. So if we have x squared, the derivative of x squared is 2x. We get that by multiplying the exponent by the coefficient. And then subtracting 1 from the exponent. If we are doing the antiderivative, we want to work our way backwards. But not only do we want to do each piece backwards, we want to do the order backwards. So if the last thing we did was subtract 1 from the exponent, then the first thing we want to do is add 1 to the exponent. Then, instead of multiplying, we want to divide, and we want to specifically divide by that new exponent. So we're going to look at some examples here when we look at derivatives versus antiderivatives. So when we look at things like what we have here, if I wanted to take the derivative of this, the derivative of 13x plus 7 is 13. The derivative of 13x minus 54 is also 13. So when we worry about antiderivatives, we need to be a little bit careful because these start out as the same thing. So when I work my way backwards, I don't know which one that they are going to give us. So when we look at these derivatives, we notice that they give us the same answer. Without an initial condition, so unless we know like a value that we can kind of work with, we'll never really know what our constant is. So without an initial condition, we will not know what version of our antiderivative we have, so we add a constant. That constant is going to be a plus c, which is why they don't really use c for a lot of things. So we're going to look at basic integration rules for us. Power rule, rules of a constant. So let's go with constant first. So if I have a constant value, any number k, and I want to take the derivative with respect to x. If I want to take the antiderivative with respect to x, or the integral, we're going to have that value k times x plus c. We have power rule. Something raised to a power, we're going to take our value of x, add 1 to our exponent, and then we're going to divide by that new exponent. If we have a multiple of some number, we call this a scalar multiple. We can take that multiple and just put that number out front. As long as it doesn't have a variable with it, we can move it out front. And then we get into some ones that we kind of use a lot. So e to the u, its derivative is e to the u, so it's still e to the u. Just like e to the u, if we have a to a power, so something that's not e, we are going to have 1 over natural log of a to the u plus c. So it's kind of like taking that derivative and doing some of the opposites of what we would have done. We don't really have an antiderivative for natural log yet, but we do have what the antiderivative of 1 over u would be. It's the natural log of u. We do need to be careful, so we put absolute values around it because the inside of a natural log, or log in general, can't be negative. The integral of sine is negative cosine, the thing that would give us sine as a derivative would be cosine, but negative. Just like how if I did the derivative of the integral of cosine, if I took the derivative of something and it gave me cosine, that something would have been sine. The integral of secant squared, so the antiderivative is tangent. I know that because the derivative of tangent is secant squared. Similarly, the integral of cosecant, or negative cosecant, if we really want to make it the exact same, we have cotangent. This one's negative because I made cosecant squared positive. The integral of secant times tangent is equal to secant plus c. The integral of cosecant times cotangent is negative cosecant u plus c. And then we have our big three. The square root of a squared minus u squared du. We're looking at sine inverse, specifically of u divided by a plus c. The integral of a squared plus u squared is equal to 1 over a tangent inverse of u over a plus c, and the integral of u times the square root of u squared minus a squared du. 1 over a secant inverse of the absolute value of u over a plus c. These are kind of like our integrals of things that we have already found the derivatives of. The one thing that I like to add here is my sine and cosine list. So I know sine, derivative sine is cosine, derivative cosine is negative sine, derivative sine is negative cosine, and derivative cosine is sine again. So if I go down this list, these are all derivatives. If I go up this list, these are all integrals. So we're going to do just some of these examples of these basic integrals and go from there. So we have find g of x when g prime of x is equal to 4x squared. G of negative 1 is equal to 3. So this one gives us an initial condition. So we're going to start off with the integral of g prime of x. The integral of g prime of x is going to be what gives us g of x. So we have the integral of 4x squared dx. We're doing power rule but backwards. So the first thing I'm going to do is write 4x. We need to add 1 to our exponent to make it 3, and then we are going to divide by 3. So we have 4/3 x cubed. So g of x, and then we need to add c to it. So g of x right now is 4/3 x cubed plus 3. We have our initial condition when g of negative 1 is equal to 3, so when x is negative 1, g of x is equal to 3. So we have 3 is equal to 4/3, but negative, because negative 1 cubed is negative, and if we multiply those together, we get a negative 4/3. And then we're going to add it to the other side. 3 is the same thing as 9/3. If I take 4/3 and add it to that side, 9 plus 4 is 13. So I have 13/3 is equal to c. So what I know is that g of x is equal to 4/3 x cubed plus 13/3. Find the position equation x of t when a of t is equal to t squared, v of 0 equals 8, x of 0 equals 4. So we have a of t, we want to take the antiderivative, the integral, and then that is going to give us v of t. Then we're going to take the integral of v of t, and this is going to give us x of t. So we have the integral of t squared. So we add 1 to our exponent and divide by it. We're going to go ahead and find that value. So we have v of 0 is equal to 8. So 8 is equal to 0 cubed over 3 plus c. This goes to 0. So c equals 8. So our v of t equation is t cubed over 3 plus 8. So this is what we're going to take the integral of. So we have the integral of t cubed over 3 plus 8 dt. We take the integral, we add 1 to our exponent, so we now have t to the 4th, and we're going to divide that by 4. We have 8t, and we have taken an integral, so we need to add a constant. This is the same thing as saying 1/3 t to the 4th divided by 4, or 1/12. T to the 4th plus 8, T plus C. Well, x of 0 is equal to 4, so 4 is equal to 1/12 times 0 to the 4th. Zero times 8, 0 to the 4th, so we get this is our final answer. These are not horrible. Once you get the hang of it, they just take a little bit of practice. So we're going to look at some more interesting ones in just a little bit.